In the last lesson, we were introduced to substitution reactions of aromatic carbons. In this lesson, we're going to focus in on the most common of these, and that is electrophilic aromatic substitution. In this webcast, we'll begin our studies of electrophilic aromatic substitution by looking at the substitution reactions of heteroatoms with benzene rings. A benzene ring with its 6 pi electrons is a site of electron density. Therefore, benzene can act as an electron donor, and most of its reactions take place with electron acceptors. In this example, benzene can react with bromine in the presence of a Lewis acid catalyst to yield the substitution product bromobenzene. The real key to electrophilic aromatic substitution reactions is generating strong enough electrophiles that can react with weakly nucleophilic benzene rings. We've seen the reaction of bromine with other pi bonds such as alkenes that did not require a Lewis acid catalyst. However, the pi bonds of a benzene ring are much more stable than simple alkenes and require the generation of a much stronger electrophile. If you're unsure of the mechanism by which benzene reacts with the electrophilic bromine species, I would suggest first to try and draw it out yourself. If you're still stuck, I would suggest rewatching Lesson 37, in which the mechanism was introduced, because it's critical to have this mechanism in your back pocket, because in this lesson we'll be strictly focused on the generation of the electrophilic species that can react with benzene. Chlorine and iodine can also be used as electrophiles in electrophilic aromatic substitution reactions. The reaction of chlorine in the presence of a Lewis acid catalyst is identical to the bromination reaction. You should be able to draw out how chlorine reacts with iron trichloride to generate an electrophilic chlorine species, and you should also be able to draw out the electrophilic aromatic substitution mechanism in which benzene reacts with this chlorine species. Iodination of a benzene ring can also be achieved by treating iodine with an oxidizing agent such as nitric acid. The key electrophile that is thought to react with benzene is shown here. Aromatic rings can be nitrated by reaction with a mixture of concentrated nitric and sulfuric acids. The key electrophile in this reaction is the nitronium ion. The nitronium ion is generated from nitric acid, first by protonation from sulfuric acid and then a loss of water. Nitration of an aromatic ring is a particularly important reaction because the nitro-substituted product can be reduced to arylamines. The arylamine can then be derivatized into a variety of compounds, and this nitration reduction route is widely used in industry. However, we'll take a look at the reduction of a nitro group in the next lesson. The last reaction we'll take a look at in this webcast is the aromatic sulfonation reaction. An aromatic ring can react in the presence of fuming sulfuric acid to introduce a sulfonic acid group onto the aromatic ring. Again, the key electrophile in this reaction is a protonated sulfur trioxide species. Aromatic sulfonic acids are valuable intermediates in the preparation of dyes and pharmaceuticals. The sulfa drug, sulfanilamide, was one of the first useful antibiotics. Drugs such as these are prepared using aromatic sulfonation as the key step.